Hi, welcome to Data Within Reach, and welcome to another Rapid R 3-minute tutorial. Have you ever wanted to take a robot, or possibly a self-driving car or a satellite, and direct it away from obstacles? You know, providing it steering inputs that keep it from crashing into a wall or the moon? Well, then this tutorial's for you. Today, we're going to create a robot object, and we're going to define a run function that uses cross-track error and a hyperparameter called tau to minimize the error in the steering input such that it travels in a stable fashion. And we'll play around with that hyperparameter to get the robot to move both in a stable way and an unstable way. We've only got about 3 minutes, give or take, so hey, let's get started. First of all, for this tutorial, we're going to use the ggplot2 library. I've already installed this package previously, so all I have to do is run the library command. If you've never used this library before, you'll need to run the install packages command and then run the library command. Next up, we create our robot class code. Now, to give full credit to where it's due, this robot class code is very similar from the Python code created by Dr. Sebastian Thrun for the class I'm taking at Georgia Tech, Artificial Intelligence Techniques with Robotics. This class was originally written in Python, but we've recreated it here in our programming language. The methods of the class are to initialize a robot with an X and a Y, an orientation, and the length of the robot. Obviously, this is a robot that exists just in two-dimensional space. We're only dealing with X and Y and an orientation, a theta value of what direction the robot's pointing. You can set those on initialization of the robot, or you can use the set method to set the X, Y, and orientation. The robot also has a move function, which uses some nice trigonometry to calculate the new steering angle, and calculate the motion based on cosine and sine of the x and y times the delta time. If you've taken trigonometry, it might look a little familiar. Lastly, there's a method to output everything to a string. Next up, we have the run function. Again, credit goes to Dr. Sebastian Thrun for the origination of this function in Python. So just to step through this function, it creates a for loop that steps through the number of times that we are going to move the robot. The function calculates the y distance to the front axle, which is the sine of the orientation of the robot, times the robot length, then calculates the cross-track error by taking the robot's y and subtracting the y distance to the front axle. Then the steering input is calculated as negative tau hyperparameter times the cross-track error. Once we have that, we pass it into the robot class that we created above with the move command. Then we use that toString method that we created and add it into the x trajectory and the y trajectory. Lastly, this function returns a list which contains the x trajectory and the y trajectory. Now that we have these, let's go ahead and create two examples, one stable robot and an unstable robot, and then let's graph those examples. So here you can say we've instantiated a new robot and set it to a location of x, y, and an angle. Now we run the robot, which gives us a long list of x, y, and orientation data. And then we run the robot with an unstable tau value, which also gives us a large amount of x, y, and theta values. Now let's take that data and move it into an R data frame, and let's combine those such that we can simply plot it. Now we'll run ggplot, and we can see the difference between a stable tau and what happens when there's an unstable tau. So as you can see with this graphic, the green line is a tau set such that the robot control is stable, and the red line is a tau set such that the robot control goes unstable, which is something we don't want.